Now that we know how to divide or reduce with radicals, we're going to start talking about rationalizing monomial denominators. We will rationalize both monomial denominators and binomial denominators, but we'll do it separately. So first, looking at rationalizing monomial denominators. So before I get into this new topic and explain how this new topic works, I want to take a step back and just do some review with radicals, and I'll kind of talk more about why after. This should be pretty easy, pretty basic for you. Square root of 7 times square root of 7 is square root of 49, which is just 7. Square root of 2 times square root of 2 is square root of 4, which is just 2. Square root of 5 times square root of 5 is 25, which is just 5. Square root of 47 times square root of 47, that's not one I know off of the top of my head, but I do know it's the square root of 47 squared. And I also know that radicals or square roots and squares cancel each other out, so it would indeed give me 47. The square root of x times the square root of x would be the square root of x squared. Again, my radical would cancel out with my square, or my square root would cancel out with my square, leaving me with just x. Square root of 3xy times square root of 3xy is the square root of 3xy, all of it squared, or I could say 9x squared y. Either way I look at, 9x squared y squared, either way I look at it, notice that my radical and my square are going to cancel, once again leaving me with just 3xy. So why is that important? Well, because we need to notice that whenever you multiply two radicals together, the radicals in essence cancel out, leaving me with just whatever it was that was under the radical, as long as whatever was under the radical, if there was more than one thing, was put in there together as multiplication. So multiplying two like radicals together, where they're exactly the same, cancels the radical. Here's why this is important. Because whenever we rationalize a denominator, let me back up. So let me give you some definitions before I tell you why it's important that we know how to do that. So a monomial is a polynomial with only one term. It says on term, but it should say one term. The terms are separated with either addition or subtraction. So in order to be a monomial, there must be no adding or subtracting. You can multiply. 2x is a monomial. 2 plus x is a binomial. So make sure you only have one term. That's all we're going to be focusing on right now. When we rationalize a denominator, we rewrite an expression so that there are no radicals in the denominator. So how do I get rid of a radical in a denominator? Well, didn't I just look at a way to get rid of radicals? I got rid of radicals by multiplying by themselves. Each time I did that, whether I had numbers underneath, a letter underneath, or a combination of letters and numbers underneath, I was able to successfully get rid of my radical. So I'm going to use that. My steps to rationalize a denominator with a monomial radical are as follows. Step 1, I will reduce first if possible. If you remember in the last video, we talked about whenever you divide two radicals, you always first check to see if you can reduce, because it makes this process so much easier. If you can't reduce, that's fine, but you'll always check to do that first. After you reduce, if we multiply both top and bottom by our monomial radical, like we saw in the beginning of this video, that radical will then go away. And then we just check to see if we can simplify using the rules we've used in the previous examples we've done either in class, on your own, or in the videos. So let's look at some actual examples where we're rationalizing these denominators. So in my first example, I have the square root of 7/5. Well, if you remember from that property I gave you in the dividing video, that's the same thing as the square root of 7 over the square root of 5. I check to see if I can reduce. 7 and 5 have no common factors, so there's nothing I can do to reduce both of them by. So the next thing I'm going to do, if you look at my flow map up here, is I'm going to multiply both the top and the bottom by my monomial radical. Well, my monomial radical that I have on the bottom here, and it's always going to be by the bottom one because the bottom one is the one I'm trying to get rid of. So I'm going to multiply top and bottom by the radical of 5. Well, this then gives me, we have already learned how to combine if we're multiplying, so the square root of 7 times 5, which is 35, all over Well, the square root of 5 times the square root of 5, like we looked at in the beginning, when I multiply two radicals, the radicals cancel. So the square root of 5 times the square root of 5 will leave me with 5 underneath. My last step, step 3, tells me to simplify. Well, 35 does not have any perfect squares in it, and I cannot reduce these because the 35 is under the radical and the 5 is not. So resist that temptation. This is your final answer. Looking at a few more examples of this. I have example 2 and 3, and then example 4. So first I'm going to look at example 2, then example 3. So I'm going to go through those same steps in that flow map. So step 1 of my flow map told me to reduce if possible. Well, I know that both 2 and 10 can be divided by 2. So this 2 is going to reduce to 1. Let me change my color. This 2 will reduce to 1. This 10 will reduce to 5. I know that x cubed over x, I'll take an x out of each one. That x will be gone. I'll be left with x squared up here. I don't have anything to reduce the y with. So I'm left with the square root of 1 times x squared all over the square root of 5, remember the x canceled, times y. So next I check, is it a monomial on the bottom? Yeah, because it's just multiplying. Monomials just make sure that I don't have any adding or subtracting, and I don't, so I'm good to go. So next thing I'm going to do is I'm going to get rid of this monomial on the bottom by multiplying top and bottom by that monomial. So I'm going to multiply top by the square root of 5y and bottom by the square root of 5y. On top, that is then going to give me the square root 5y times x squared is 5x squared y. Remember, it does not matter what order we multiply in, so I could have written x squared 5y. I just tend to put my numbers in the front and then put my letters in alphabetically. The square root of 5y times the square root of 5y. Well, if I multiply two monomial radicals together, the radicals or the square roots disappear, leaving me with just the 5y. That's called my radicand. From here, I check to see if I can simplify. Well, I know that the square root of 5 does not have any perfect squared. I know that the square root of x squared, whether I write it as a fraction or go by grouping, is going to reduce to be just x, leaving me with, so x squared is going to become x. You can think of it as 2 over 2, or you can think of it as if I have 2, I make one group, times the square root of 5y all over 5y. I check to see if I can reduce, but because this is under a radical and this is not, there is not anything else I can do with it. These are both not under radicals, but x and 5y don't have any common factors, so this would be my final answer. If I look at example 3, I'm going to do the same thing. If you wanted to try and pause and see if you could simplify this on your own, this would be a great example to do that one on, because example 4 is going to be a little bit different. So first thing I'm going to do is check to see if I can simplify, and I know that x to the 5th can be divided by x squared, giving me the square root of x cubed. I can't reduce the 18 or the y to the 5th, so those stay. Next thing I'm going to do is now I'm going to go ahead and multiply top and bottom by that monomial in the denominator, 18y to the 5th. So I'm going to have, and I'm going to go ahead and write this down here since I'm running out of room on the side, the square root of x cubed over the square root of 18y to the 5th, both top and bottom being multiplied by the square root of 18y to the 5th times the square root of 18y to the 5th. Let me do this so that my work doesn't get mixed together. Well, when I do that, notice I get on top 18x cubed y to the 5th all under the radical over, my square roots cancel out when I multiply them twice, 18y to the 5th. Now I have to ask myself, can this be simplified? Well, I know that the square root of 18 can be broken into the square root of 9 times the square root of 2. X cubed, I'm not, depending on which method you like, you can either think of it as if I have 3, I can pull one group out and have one left over. If I have 5, I can pull one group out and have 2 left over. If you like exponents, I would have x to the 3 over 2 y to the 5 over 2 all over 18 y to the 5th, giving me 3 times the square root of 2. 2 goes into 3 once, and 1/2. The 1/2, I'm running out of room, so I'm going to anticipate that that 1/2 is going to change back into a radical, so I'm going to do it now. Y to the 5 over 2, 2 goes into 5. 2 whole times with 1/2 left. I'm anticipating again that that 1/2 will go back under a radical, so I'm going to do it here. All over 18y to the 5th. Well, if you remember this then, before, first this becomes 3xy squared, square root of 2xy, all over 18y to the 5th. If you remember, I said before that I could not reduce. So I'm going to come up for a second and this is going to go away, but I couldn't reduce anything to begin with. I couldn't reduce anything other than the x to the 5th and x squared to begin with. But if you remember on your flow map, my third piece says to simplify. Well, I've simplified a little bit. I simplified the square root of 18. I simplified the square root of x cubed. I simplified the square root of y to the 5th. But can't this be simplified further? Can't 3 and 18 both be divided by 3? Can't y squared and y to the 5th both have 2 y's or y squared canceled out? Giving me my final answer of the 3 cancels. X, the y squared cancels. Square root of 2xy. On the bottom, when the 3 and the 18 canceled, 18 came to 6. When y squared and y to the 5th canceled, y to the 5th became y cubed. And there would be my final answer in its most simplified form. Looking at one other type, I have here the cube root of 4 over the cube root of 6x. First thing I still do is check to see, can this be simplified? And I notice they can both be divided by 2, giving me the cube root of 2 all over the cube root of 3x. Now, before I go any further, I need to point something out. When we did the square root of 2 times the square root of 2, we got just 2. It's a little bit different with cube roots, and here's why. If I did the cube root of 2 times the cube root of 2, that would give me the cube root of 2 squared. 3 and 2 do not cancel, or in other words, the cube root of 4. 4 isn't a perfect cube. I'm still stuck with a radical. But what if instead I did the cube root of 2 times the cube root of 2 times the cube root of 2. Wouldn't that then give me the cube root of 2 cubed? Or the cube root of 8? Either way I then look at it, the cube root of 2 cubed, my cube root and my cube will cancel, leaving me with just 2. The cube root of 8 is 2, so regardless of which of those two forms I use, I get just 2 and my radical has disappeared. So my index tells me how many times I have to multiply that thing by itself in order for the radical to go away. It works the same way with variables. Cube root of x times cube root of x times cube root of x equals cube root of x cubed. The cube root and the cube cancel, leaving me with just x. So I'm going to use that idea up here on example 4. So I'm going to go ahead and rewrite what I already have, which is the cube root of 2 over the cube root of 3x. Now I know that in order to rationalize this denominator and get rid of my denominator of cube root of 3x, I'm going to have to multiply it by cube root of 3x 2 more times. I need 3 total in order to get rid of my radical. I started with 1, I put 2 more on there. But now think about your fraction rules. Anything you do to the bottom, you also have to do to the top, which means I'm going to have to multiply this by cube root of 3x twice as well. When I do that, I now have 2 times 3 all under the cube root. So 2 times 3 is 6 times 2 more is 12. X times x is x squared on top. On the bottom, cube root of 3x times cube root of 3x times cube root of 3x is just 3x. If I look, could I simplify it any further? Well, does 12 have any perfect cubes in it? not divisible by 8, not divisible by 27, so no. If I have 2, could I pull out any whole groups of 3? No. Or if I rewrote this in fraction form as 2/3, could I change that to a mixed number? No. I cannot reduce the 12 and the 3. 12's under a radical, 3's not. I cannot reduce the x squared and the x. X squared is under a radical, x is not. Therefore, this is my final answer.